About full area repeatable articulator. The full area repeatable articulator will be described in this order. Explain the head diagram in 1. This video is illustrated using CATIA. This image is a mesh model of the human head that will be used for the explanation. It can be divided into left and right sections. The upper and lower dental models are set up inside the head. This upper and lower dental model is mounted on an articulator. This allows the mandible to be exercised. Hide the right half of the head. Displays the maxillary and mandibular frames of the articulator. This articulator was used to obtain mandibular movement data from the living body, but will not be used this time. We will use a simulator, a very small articulator that functions in a similar way to this articulator. This ultra-compact articulator will be introduced later. Principles of the full area reproducible articulator, in 2, will be explained. This is the coordinate system of the articulator. It is based on the origin here. Enlarge this ultra-compact articulator. An ultra-compact simulation articulator is shown. This articulator is for CAD only. It does not function as an actual articulator. CAD-only simulators are related to the measurement method. The measuring instrument had not yet been explained. I have yet to explain how to measure in front of the lip. Initially, I was going to describe how to measure mandibular motion using 2 check bites per side. However, as I proceeded with the preparatory work for the explanation, I changed my mind. I have come to believe that the method of obtaining continuous mandibular movement data by measuring in front of the lip may have a wider range of applications than the method using a check bite. Although we have not actually created a measuring instrument and this is a matter of consideration, we will explain how to collect and reproduce continuous mandibular movement data. The movement data used in this explanation was obtained by using 2 check bites per side. The origins of this ultra-compact articulator have to do with the way data is collected. The tool to reverse engineer, or reproduce, the collected data is this ultra-compact articulator. Indicates the measuring instrument. It is in the form of goggles used for virtual reality. Show the head. Shows the relationship between the head and the equipment used to measure mandibular motion. Hides the articulator. Displays the probe for the measurement. Enlarge the probe. Hide the ultra-compact articulator from the model tree. It has a triangular base with 3 points. On CAD, they are colored green, red, and yellow. The housing part of the probe is forward and does not cover the probe. Measurement cannot be made in this condition. After the probe is connected to the oral cavity, move the housing carefully so that the probe does not contact the housing when the mandible is moved. The housing covers the probe. Fine adjustments are made so that the probe does not contact the housing when left and right lateral and forward movements are made. We have shown that there is a coordinate system for the articulator and a coordinate system for the measuring instrument. The congruent relationship between the measuring instrument and the ultra-compact articulator is also shown. We will now show the principle of the coincidence of the coordinate system of the articulator and the coordinate system of the measuring instrument. Regarding the coincidence of 2 coordinate systems, calibration. The definition of calibration is as follows. 1. The correct adjustment of the scale of an instrument. Calibration. 2. To compare whether the values indicated by a measuring instrument are correct or not using a reference standard or standard sample, and to correct the differences. Calibration in this case is to match the coordinate system of the articulator with that of the measuring instrument. In principle, the check bite can be done in one place. As you saw earlier, 3 points are assigned to the tip of the probe. Thus, a plane can be defined with a single check bite. For example, this can be done with a mashed bite taken in the central occlusal position in the oral cavity. Specific methods. 1. Wear the headset. The mash bite is taken intraorally and recorded with the electronic stamp on the headset at the same time. 2. In principle, the mash bite data obtained in 1. above and the location data recorded by electronic stamping are identical. The word "in principle" means that in reality, there is a possibility of error. 3. This allows the coordinate system of the articulator to match the coordinate system of the measuring instrument. No matter how accurately data is collected, it is meaningless if the data cannot be accurately captured in the CAD. The probe triangle on the mandible model of the articulator in CAD and the electronically stamped triangle will match. 4. All data collected while wearing the headset can be applied no matter how many mandibular movement patterns are collected. 5. However, if the headset is once removed and reattached, it must be calibrated anew. 3. 2 specific examples. Data measurement. We have tried to devise a helmet type and a virtual goggle type. We will provide details about the virtual goggle type. 1. Overall composition. Overall view of the headset. This CAD model was created by downloading shape data of goggles for virtual reality from a free download site and modifying some parts of the model. Look at the object from above or below. The goggles are attached and detached by a rubber belt. There is also a type of belt that covers the top of the head, but it is best if it can be secured so that it does not shift. Set the probe so that it does not touch the sensor housing. 2. Smartphone-like video display body. Hide the goggle cover. The smartphone is contained in the equivalent of the screen of the goggles. Images can show the patient's mandibular motion guidance during data measurement. It does not actually have to be a smartphone. The dentist verbally guides the patient through the mandibular movement. In addition, the use of video images will make it easier for the patient to understand and feel at ease. 3. Probe and splint. Temporary fixation. Hide the left half of the head. Hide the maxillary model. This orange portion is the splint. It holds the probe in place in the dentition and is made of resin or other material. Care should be taken not to interfere with the maxillary teeth. 4. The relationship between the housing and the probe. Hide the head. Enlarge the housing section. Hide the maxillary model. The 4 black cylindrical objects on the housing are sensors. We assumed that the sensors would be cameras, but we have not yet come up with a specific method. The number of sensors could be less. We would like to ask for the best approach from those who can make this happen. 5. The relationship between the probe and the ultra-compact articulator. Hide the housing. Shows ultra-compact articulator. Enlarge the ultra-compact articulator. The ultra-compact articulator and probe overlap. Hides the body of the probe. The 3 green, yellow, and red points on the body of the probe and the 3 left side condylar point, right side condylar point, and incisal point on the ultra-compact articulator coincide. By matching the 3 points, the reproduction of the mandibular path of motion can be reverse engineered. 6. Measurement data. Change the mode displayed in CAD from assembled mode to kinematics mode. Simulate mandibular motion. One process is recorded in 1001 frames and played back at 5x speed. A reciprocating right lateral movement has begun. The driving method for this simulation is the center method with a large articulator. This is the movement of the non-working side of a large articulator. Move to the center section of the large articulator. This is the center section of a large articulator. When simulating mandibular motion, one drive location is required. It can be set at the working condyle head, at an extended location on the working side, or at a point midway between the left and right condyle points. Move to the measurement section. The probe moves in accordance with the movement of the patient's mandible. The probe is given 3 points, and its movement is captured and recorded by a video element. Mandibular motion is a difficult high-level task because it is a three-dimensional movement. It will also require a great deal of precision. We do not have any specific ideas on what kind of sensors to use or how to record them. I am not knowledgeable enough to mention that much. I would like to ask someone who can make this happen. Next, we introduce a helmet-type measuring device. 1. The overall configuration. This is a helmet-type measuring device. Goggle-type instruments had a smartphone-type screen display, but helmet-type instruments do not. Enlarge the probe and housing section. Helmet-type probes have only one measuring point in the anterior part. Therefore, there is only one point. Go to the measurement section on the left. The measurement section on the left also has a housing covering the tip of the probe. Go to the measurement section on the right. Magnify the probe on the right. The probes are now distributed in 3 locations: front, left and right, and naturally, the sensors are also distributed in 3 locations. 2. Probe and splint. Hide the helmet section and housing section. Overall view of the probe, with the probe points distributed in 3 locations. It resembles a conventional style pantograph. I can't say for sure because I haven't actually built a measuring device, but a probe with a larger distance between the 3 points for detecting mandibular motion will be heavier. Depending on how the patient moves the mandible, there is a great potential for vibration and errors in measurement. This is the connection to the splint, fixing section. Since the probe is now heavier, the splint is also subjected to a greater load. The probe should be as light as possible. It is easier for the patient to move the mandible if the probe is light. 3. The relationship between the housing and the probe. The probes are distributed in 3 locations. Therefore, the video element sensors must also be set up at 3 locations, which is also expensive. In addition, the positions of the 3 housing locations must be adjusted for each individual patient. Therefore, the setting may be troublesome. The housing should not make contact with the probe when the mandible is in motion. This is the sensor section on the right side. Since this is a schematic design, the adjustment mechanism is not fully described. Adjust the position of either the housing or the probe. This is the sensor on the left side. Since the probe is now divided into 3 locations, the position of the sensor must be fine-tuned for each individual, creating the problem of how to integrate the 3 separate coordinate systems. If you are only obtaining mandibular motion, the line segment connecting the tips of the left and right probes need not coincide with the axis of rotation defined by the centric relation. I believe the goggle method introduced earlier is superior in terms of accuracy and instrument handling. However, a high degree of accuracy is required. 4. Measurement data. Change the mode displayed in CAD from assembled mode to kinematics mode. Regarding the location of the sensor setting points near the left and right mandibular heads, there is no such thing as setting the measurement at the hinge axis position. In this example, the virtual kinematic axis method is used. Therefore, it is sufficient to place the sensor near the mandibular head. This is the anterior reference point. The motion path has already been obtained. One process of mandibular motion is reproduced with 41 points. Since the virtual kinematic axis method is used, it is sufficient to say, approximately this position. Non-working side. Exercise data has been obtained. Regarding the motion of the probe's condylar portion, the path of motion is considerably more lateral than the actual path of motion of the biological mandibular head. Since the virtual kinematic axis method is used, there is no problem. This is the work side. It is well outside the actual pathway. The motor pathway shows a complex pathway. Change the viewpoint on the work side. This three-dimensional motion cannot be represented by motion on a plane. To reverse engineer accurately, it is necessary to obtain synchronization points. Relying on the synchronization points, the formula can be used and reproduced. Results of the study. The title of the video says, Full Area Repeatable Articulator. Why do I claim that this is possible? The reason for this is in the way the motor paths of mandibular movement are recorded. Since it is recorded electronically, it would be possible to record multiple numbers of mandibular movement paths. It would be possible to record all kinds of movements, not only lateral movements to the left and right, but also anterior movements and opening and closing movements of the mandible. In left and right lateral movements, one type of movement is usually obtained for each side, but any number of types can be recorded. From the results of these considerations, it may be possible to study centric relations, which are difficult to define, objectively and not just rely on human senses.